Perfect timing. Any other questions or reminders I need? Okay. Reaction 11. So we are going to get into a series of reactions at the end of this chapter. So there's 16 reactions in total. And we're going to talk about the last handful here. And they all look kind of busy. The first couple that we're going to talk about, though, look worse than they really are. And then the last three are fairly busy. The nice thing, though, about these last 5, I think it would be, yeah, you don't need to know the mechanisms for them. We will talk a little bit about the mechanism so you can understand what's happening, and it might help you picture what's happening, but you don't need to know them for the test. So the first one we're looking at is called the Malonic ester synthesis. And it's called that because we're starting with malonic ester. Now, malonic ester, of course, is not its actual name, it's its common name, but it sticks. We're going to react that with base, and notice that the base we're using is the same as the OR group on that ester, so we're using N-ethoxide. And what that base is going to do is it's going to take off one of these alpha hydrogens. So we're going to end up with this as a nucleophile. So this is after step number 1. Step number 2. Step number 2, in terms of like synthesis, is our most important one because it's the only thing we have control over. So we have to use malonic ester. We have to use ethoxide. The last step has to be acid, water, and heat. Here's the only thing that we get to decide. We're going to react it with an alkyl halide. And even with that, our alkyl group has to be a methyl or a primary because we're going to actually do an SN2 reaction on this. We're doing a nucleophilic attack, loss of a leaving group. So, and the malonic ester is already pretty big and bulky, so we need to use something that's fairly small, methyl or primary. And so at this point, after step number 2, we have our double ester. I'm going to run out of space. I'm going to go up weird there. With an R group attached to it. So then in our last step, we're going to react it with acid, water, and heat. The acid and the water are going to turn our ester into a carboxylic acid. And we know that. We know that that's what happens when we react an ester with a when we react an ester with acid and water. We learned that in our last chapter. But there's also the addition of heat here. That heat's going to cause what's called a decarboxylation. And so look at what we end up with in our final product. We have a carboxylic acid with a new R group attached. So what we are keeping is, actually, let me draw the circle around the other half so it's facing the same direction. That's the part that we're keeping. The 2 circles match up together, and then we're just attaching an R group to that alpha carbon. The other carbon, the other ester carbon, first turns into a carboxylic acid, and then with the heat actually breaks off and turns into a CO2 group. So I'll show you that on the next slide. I'll show you the mechanism to go along with that. We can actually do this twice though. So the bottom reaction is showing our malonic ester, so same starting material, always has to be the same if we're doing this reaction. We're going to react it with base, R group, base, R group, and then step number 5, if we had this all written out as one, is acid, water, heat. And so then we can add the 2 different R groups, or it could be 2 of the same. If we wanted to have 2 of the same R groups, we would still have to do it twice though to get 2 of the same on there, but get those 2 R groups attached at that alpha carbon. Here's kind of a mechanism. I say kind of because we're cheating a little bit in the middle. But this is step number 1. We're using the base to remove that alpha hydrogen. Step number 2 is that SN2 reaction. So we're doing a nucleophilic attack, loss of a leaving group. And then in step number 3, we're turning both of our esters into carboxylic acids. And right here, it's a reminder that we've seen this before. This was mechanism 20.8 in our last chapter. So we've seen this. I think it was on our test. It was either this or the other way around. I can't remember which one now, but you've seen this. Here's that heat step. So here's our heat portion. The minus CO2 tells us that CO2 is leaving. So that's not a reagent. So I've kind of said this before, when it's written that way, it's a little bit confusing. But here's our structure. So this and this are the same thing. It's just rotated around a little bit. The carbonyl grabs onto that hydrogen. It causes a domino effect. So actually, let me erase that so I can talk about it as I do it. As this arrow goes right here, it's making a new carbon-oxygen double bond. And then this arrow right here, this last one that I'm highlighting, is probably the most important one because it's breaking that carbon-carbon bond. So it's breaking the bond between the alpha carbon with the carboxylic acid and then the rest of that CO2 group. So the portion that breaks off is right here. That becomes CO2. And we know we've talked about before that when we make a gas as like a side product, it's always good because it just kind of bubbles away and goes away, helps push that reaction forward. The product that we get from this is the enol. And one of the first things we learned in this chapter was the tautomerization process. So that enol tautomerizes into the carbonyl version. And there's our R group that we've added on. So this goes from, I'm going to go back one slide. I have this written as going from an alkyl halide to a carboxylic acid, which is slightly misleading. But the way I have it, the reason I have it written that way is because the alkyl halide is the only thing that we get to decide. The ester portion, the base, the acid and water, that's all set reagents. So we get to decide what that R group is and attach it to a carboxylic acid, essentially.
Am I still an alien, or can I actually ask a question?
Oh, I can hear you just fine. You've lost your alienness.
Oh my goodness. The clouds have parted. So for this twice section, right, where you have the NaOET RX twice, does that mean that you actually have to like take your product and then separate it and then do the reaction all over again? Or does it mean you put in twice the amount of one of the precursors?
It does mean you'd have to separate it out and then do it all again. Because if we just kind of dumped it all in there, so with, this one's red and blue. So you might end up with some that have 2 red R's or some that have 2 blues, when in reality, we would want one of each. So we'd have to be very careful with adding in one equivalent, doing a workup, getting rid of the excess if there is any, and then adding in that second one. So it would be annoying to do in real life for sure.
Gotcha. Okay, so this is another one of those things that probably doesn't have the highest of yields.
No, definitely not. Any other questions on this one?
The more we go into reactions like this, the more I wonder, in higher levels of chemistry than this, how anyone gets any amount of yield with so many different products that are possible.
Yeah, it's not easy, that's for sure. If you read, especially like organic synthesis journal articles, they will end with like a 12% yield. And if you see like a big long chain of reactions showing this is what we started with and we went through 15 reactions to get to our product, each product will have the percent yield underneath it, and it just gets lower and lower and lower. So yeah, it's frustrating for sure. Okay, the next one is super similar. And then we're gonna do I have a practice one. I can't remember if I have a blank slide for it. If not, we'll put one in. Our next one, reaction number 13, is called the acetoacetic ester synthesis. And again, the name is because we're starting with acetoacetic ester. So really, the only difference between this one and the malonic ester synthesis is that on our malonic ester synthesis, we have an ester on each side. With this one, we have an ester on one side and a methyl group on the other. The process, what happens, is going to be super similar though. Starting with base, and again, we're using ethoxide because we have that ethoxide attached to our ester. Here's that alkyl halide. It's going to be an SN2 reaction again, so it still needs to be a methyl or a primary. And then acid water heat, and what that's going to do is it's going to chop off this portion over here, and we're going to end up with a methyl ester. So we get to keep this part. That's the part that's highlighted in yellow over here, and then we're attaching the R group to it. So we will always end with I think I said methyl ester a second ago. I meant to say methyl ketone, sorry. We will always end with a methyl ketone, meaning a ketone that has a methyl on one side, because that's what one side of this acetoacetic ester is. In terms of the mechanism or the pathway, I'm going to go back one slide. Let's see what color is not on this. I don't have any green. If we turn this into an acetoacetic ester synthesis, I'm just going to go through and replace this ethoxide on the left side with a methyl. And now it is the acetoacetic ester synthesis. So it's the exact same process. It's just that we only have one ester that's turning into a carboxylic acid. So that has to be the one that breaks off and becomes a CO2 group. And the other side stays a methyl ketone. It's not affected by that acid and water. No, they are not starred. I'm just talking about the mechanism to help you see what's happening, help you learn it. Questions about this one? Okay, let's see. Do I have a blank? I don't have a blank. So let's add one in. I thought I did. I must have just made space earlier. Oops. Sometimes I write too big with intentions on doing a practice problem. So we will do it with malonic ester. And actually, we're going to do what's called a retrosynthesis. So I'm going to tell you that this is a malonic ester synthesis. And I'm going to show you what the product is. And we have to figure out the starting material. Nope, wrong carbon. I think that's right. Okay, I think I'm good.
So this is the reaction 12?
This is reaction 12, yes. Normally, I tell you guys not to worry about the reaction names. This chapter is the only exception to that. So on this test, I will have questions like this, where it will be like a retrosynthesis and you have to fill in all the missing reactants, reagents. The last handful of reactions we're looking at are super similar to each other. So in order to kind of guide you down the right pathway, I will tell you what the name of the reaction is. I will tell you which pathway you're supposed to be on. That is meant to help you. So to have it help you as you are making flashcards for these or rewriting them, studying them, make sure that you're including the names with them. When I type up the study guide, I will tell you what names you need to know. But for right now, assume that it is reactions 12 through 16. So the last 5 reactions. Okay. Because it's malonic ester, we know what we have to start with. We have to start with malonic ester. We don't have a whole lot of options there. We also know that when we do a malonic ester synthesis, we're going to end with a carboxylic acid, and then we can have stuff attached at that alpha carbon. So when we look at what we're ending with, there's my alpha carbon. So it looks like I need to do the reaction twice, because there's one substituent. That could be our first R group. And there's our second R group. So because we have 2 things attached to that alpha carbon, that tells me that we need to go through the reaction 2 times. But we know how to do that. We're going to start with our base, NaOET, or we could just write minus OET. That would be okay. Number 2, we're going to add in one of those R groups. It doesn't really matter which one. I grabbed the green pen, so I'm going to do the one that I have boxed in green first. So make sure that you're not cutting any carbons off. I have a benzene ring with 1 carbon. So I have a benzene ring with 1 carbon with that halogen attached to it. And then my base, I'll write the base the other way, just so you can see it written out both ways. And then we need our second R group. And again, over here, 1, 2, I have 3 carbons. So bromine, 1, 2, 3 carbons. And then our last reagent, acid, water, heat. So I'm just going to combine my acid and water to write H3O plus and throw in some heat. So everything that's in blue in that box are set reagents, nothing that you can change or have control over. The green and the orangey yellow are the R groups that can be changed based on what we're trying to make. Questions about that reaction at all, about that example? Okay. Oh, why did you use Na? So I used Na, yes. Yeah, it was just essentially just to write it out different so that you could see the different ways to write it, even though they are exactly the same. Yeah. Sorry, I probably made it more confusing than helpful. Adjusting a little here. Okay. We are going to look at 3 more reactions, and we're going to continue to react that alpha carbon, but what we're reacting it with is going to change slightly. So we're going to start using alpha beta unsaturated carbonyls. And notice we're using the word carbonyl there. We're being pretty generic because there's going to be some wiggle room with what can be used. The resonance that is on here is showing us how we're able to do the reactions we are. Now, again, these last 3 reactions, you do not need to know the mechanisms for them, but seeing them and kind of walking through them can help you understand why things are happening, which can help you learn them and remember them. So if we look at the resonance hybrid for this aldehyde, this alpha beta unsaturated aldehyde, here's my kind of basic structure. Remember when we draw resonance hybrids, we draw the little dashed line to show where the shared electrons are moving to and from. And then we do partial charges. So the oxygen is partially negative and the carbonyl carbon is partially positive. So that's essentially right there is why we had chapter 19. We had nucleophiles that were attacking the carbonyl carbon. When it's alpha beta unsaturated, though, we also have a partial positive charge on the beta carbon. So alpha, beta, which means that that carbon can also be an electrophile. So we're going to look at some reactions that react our alpha carbon of one molecule to a beta carbon of a alpha beta unsaturated carbonyl. And I'm going to redraw that resonance hybrid on the next slide. Okay, there's my hybrid. There's kind of a competition happening, and I'm going to briefly mention this. The book goes over it a little bit more. It's not something that we need to worry about too much. I want to point it out, though, so that when you do see it in the book, or if you see it on other videos or something, you understand what they're talking about, but also what side we're focusing on. Right here, this was chapter 19. A strong nucleophile will do a 1,2 addition. And when it says a 1,2 addition, it's referring to adding something to the carbonyl carbon, that would be 1, and adding something to the oxygen. So when we did our aldehyde and ketone chapter, we attacked that carbonyl with a nucleophile and added a hydrogen to the oxygen. We call it a 1,2 addition because they are that close to each other, the oxygen and the carbonyl carbon. 1, 2, very close. When we have an enolate, we're going to get a mixture of a 1,2 and a 1,4 addition. So the 1,4 addition is when our nucleophile is now attacking the beta position, 1, 2, 3, 4, and then we add a hydrogen to our oxygen. So again, the numbers are just telling us how far away they are from each other. The last bullet point, though, is where we're going to be focused. When we have a stabilized enolate, we only get the 1,4 addition. This is our focus. So yes, there's competition. Yes, there's another reaction that can happen, but we've already talked about that reaction. We talked about that reaction in chapter 19. So it exists. There is some competition, but we are focusing on just the 1,4 addition. So down here is showing us that 1,4 reaction. Our nucleophile is attacking that beta carbon, which would be position number 1 in the 1,4 label. And then we have some electron rearrangement. So the pi bond shifts, both pi bonds shift, and we end up with our enolate. Then we add a hydrogen to our oxygen, and that's the 4. So 1, 2, 3, 4. We get our enol. So remember, the only difference between the enolate and the enol is the charge. The enolate's negative, the enol is neutral. The enol is not the stable version of our product, though. So it's going to tautomerize into the carbonyl version, in this case an aldehyde, the carbonyl version of our product, because the carbonyl version is the more stable form for the most part. We saw some exceptions to that, but for the most part, the carbonyl is the most stable. So after all of that, look at what really happened to our product over here. We added a nucleophile at the beta carbon, and we added a hydrogen at the alpha carbon. There's a lot of resonance and tautomerizing and rearrangement that happens, but really we're just adding something to a double bond. We've seen this happen before. We had a whole chapter on alkenes. There's just a lot of extra stuff happening with this, so we got to kind of look at why. So let's look at what that nucleophile is going to be and look at some specific reactions. So our first specific reaction is called the Michael reaction. To do a Michael reaction, we need a Michael acceptor and a Michael donor. The Michael donor is our nucleophile. So this is our, let's see, this is our Michael donor. It's a stabilized enolate. So it said that on the last slide that a stabilized enolate will do the 1,4 addition. For us, a stabilized enolate is a 1,3 di, and I'm going to put dicarbonyl here. This is a diketone, but again, there's a little bit of wiggle room with what we can use, so I'm just going to be a little bit more generic there. And then our Michael acceptor is our alpha beta unsaturated carbonyl. So there's our Michael acceptor, and this is our electrophile. So here's how we do our Michael reaction. First step, base. That base is going to take off that alpha hydrogen, and we end up with our enolate. Second step, we add in that alpha beta unsaturated carbonyl, the Michael acceptor, and we react at that beta position. The rest of this mechanism is essentially what we saw on the last slide. Things move around. We add the acid and the water to turn the enolate into an enol, and then it tautomerizes back. What we end up with, though, as our product is this thing, kind of big and bulky. It's labeled as a 1,5-dicarbonyl, which seems a little misleading because technically there's 3 carbonyls on there. So you might wonder, well, why is it not called a tricarbonyl? 2 of those carbonyls were already on the same structure. So when we say 1,5-dicarbonyl, we're talking about how far apart the 2 carbonyls are that weren't on the same structure to start with. So 1,5-dicarbonyl. The new bond that has formed is this one right here. So we formed a bond between the alpha of our Michael donor and the beta of our Michael acceptor. The only other change that occurred is that double bond is gone as well. So we formed that new bond between alpha and beta, and we lost the double bond. So it kind of seems like there's a lot to draw, a lot that can happen, but it really is just one bond that is combining together. I mentioned that there was some wiggle room. So we have a list of Michael donors. We looked at this first one. We looked at a 1,3-diketone. It could also be a 1,3-diester or a beta-ketoester. These are the 3 that you should be able to work with. The other ones, the cyano, the nitro, this last one is technically a Gilman reagent. You won't see those 3 on the test. They're just kind of a little bit out there. I want you to focus on what this reaction's doing as opposed to how weird it can get.
Professor, I have a question.
Yeah, go ahead.
So for the slide up back one, how does the H3O plus, what does it do to the pi bond on step 2 again?
Okay, I'm gonna go back one more slide. This nucleophile, that's the alpha carbon of the 1,3 diketone. So that's this guy. Whoops. So our pi bond initially just kind of shifts around and we end up with our enolate. The pi bond goes away because the enol tautomerizes into the carbonyl. So that pi bond eventually becomes part of the carbonyl again. That's where those extra electrons go.
Okay, thank you.
You're welcome.
What would be the 1,2 product in that instance?
For this one?
Or no, I'm sorry, for reaction for the, oh goodness, conjugate addition reaction. Yeah, that one.
So for this one, the 1,2 would be to have the nucleophile added at the carbonyl position and the oxygen turning into an alcohol. Because adding the nucleophile at carbon number 1 and then adding the hydrogen at position number 2, which would be the oxygen.
Gotcha.
Any other questions? Okay, so the other half of this table are the Michael acceptors. And see, I'm going to label this as electrophiles, which means I'm going to go back over here and label this as our nucleophiles. In our Michael acceptor section, on the last slide, I labeled these as alpha beta unsaturated carbonyls. So we looked at alpha beta unsaturated aldehydes, but there's also ketones, esters, amides. Again, those are the 4 that you need to know. We also have cyanos and nitros. You won't see those on the test. They're getting a little bit weird, a little bit outside of the pattern. So those would be the 4 that we need to know. We're going to do a practice one with this. And we're going to look at one that has an ester because the esters are going to do something similar to what we saw with our first 2 reactions. We're adding acid and water in the end, so we know what that's going to do to an ester or an amide. So we have to we can't look at the reactions with blinders on anymore. We know too much. So we have to think about how everything will be affected. So let me find which slide I'm on here. Here we go. And this is a Michael reaction. And I point that out because this looks very similar to the start of our acetoacetic ester reaction. Here's where the difference is, though. With acetoacetic ester, we would react this with an alkyl halide. But with a Michael reaction, we're reacting it with an alpha beta unsaturated ketone. All right, so we're going to fill in the product. It is a lot easier than what it looks like. Our base is going to grab the alpha hydrogen. And I'm kind of doing like a half-assed mechanism here because, again, it can kind of help you see what's happening. And then I'm going to redraw my alpha beta unsaturated ketone 2468, 2468, making sure I had enough carbons there. I'm going to draw my new bond in green. The new bond is going to happen from our alpha carbon to our beta carbon. and that double bond is going to go away. That's the new bond that occurs. So this is not quite my final product yet, but it is almost there. One, two, three, four, five, six, seven, eight. So just counting my carbons in my what was my alpha beta unsaturated carbonyl to make sure that I didn't lose anybody along the way. Now in that final step, we have acid and water. We know that acid and water turn a carboxylic acid, or excuse me, turn an ester into a carboxylic acid. So here's what our final product is going to look like. We're going to have a carboxylic acid on the end instead of that ester. But that's the only other thing. No, that was not a pretty structure. Let's try that again. That's the only thing that will change. Questions about that product? So if you just want to think about, I'm going to do a quick little erase here. If you just want to think about these two stacked on top of each other like this, like I've done in a couple other reactions, and we draw in that new bond and you, oh, do I have an undo option? I don't think I do. Let's see, Control Z. Nope, that definitely didn't do it. Darn it. Okay. What did I get for trying to cheat? There we go. Okay, let's try that again. So if you stack them on top of each other and go from alpha to beta and delete the double bond. Oh man, there we go. That will give you your basic product. And I say basic product because then you have to look at what else is in the structure. If you have esters or amides, they're going to turn into carboxylic acids. There's one more thing we got to bring up right here though. What if in that third step, we also had heat? So acid, water, and heat. In our malonic ester and acetoacetic ester syntheses, we saw that heat can cause a decarboxylation. So if that's included as a reagent, we're going to lose this carboxylic acid group. And so our final product would look like that. So this is the decarboxylation. Ran out of space. So that's only if there is heat in there though. Without the heat, we keep the carboxylic acid. Questions about that?
Does the ketone and the aldehyde just stay the same? Those don't form the carboxylic acid?
No, it's just the carboxylic acid derivatives that go through that process.
Okay, thank you.
Mm-hmm. Yeah, so let me go back to that table. Any of our aldehydes or ketones would stay intact as an aldehyde or a ketone, but our esters and our amides would turn into carboxylic acids. Anything, and this does still follow. Remember the way that the product for this was labeled was a 1,5 dicarbonyl. it still fits that label. It still fits that product description. Okay, anything else on this one? All right, then let's look at our next one. Our next one is super similar, but it doesn't seem like it at first glance. We want to do essentially the same reaction, but instead of using a diketone to start with, we're just going to use a regular ketone. But a regular ketone isn't going to have a very stable enolate. So to make it more stable, we're going to turn it into an enamine to start with, and then eventually we will also get rid of that enamine. So enamines were also back in chapter 19. If we react a ketone with a secondary amine, and one that's very, so because the enamine's not our final product and we're eventually just going to get rid of it, putting 2 R groups there is completely okay because we don't care what the R groups are. But a common one that you will see, whoops, is this. So having a 5-atom ring with the nitrogen in there, because it keeps it all kind of contained. There isn't like a chain that's going to get in the way of anything else. So that's a really common one. The bottom down here is showing the resonance structures of that enamine, and we end up with a negative charge on that alpha carbon in one of the resonance contributors, which means that in our resonance hybrid, that will be a partial negative charge. So that is our nucleophile. So here's how we're going to use this. This is called the Stork reaction, by the way. So these last few, Michael, Stork, they're all, of course, named after people. This is 3 steps. First step is to make the enamine. So we have to use a secondary amine, some acid. So this is an acid catalyst. That's why it's in brackets. It's telling us that it's a small quantity. This is just telling us that we're losing water. That's not a reagent. It's not really helpful information. So I'm crossing it off. Second step is a Michael reaction. So this is our alpha beta unsaturated carbonyl. So when we combine an enamine reaction with a Michael reaction, we get a Stork reaction. And then last step is hydrolysis. So acid and water, probably our most used reagent there. The acid and water is doing a couple things for us. It's doing the same thing it did in the Michael reaction, meaning it turns our enolate into an enol, and then our enol can tautomerize back into the ketone. So it's helping with that. But it's also turning our enamine back into a ketone. So the acid and water is doing double duty for us. Here's where we're actually forming the reaction. This alpha carbon on our ketone is going to form a new bond to the beta carbon of our alpha beta unsaturated carbonyl. So it's the same thing we saw in our Michael reaction. This right here is our new bond going from the alpha to the beta. And 1, 2, 3, 4, 5, we're still making a 1,5 dicarbonyl, because this really is a Michael reaction. It's just a specialized type of a Michael reaction. So it's just getting more specific. The product's going to be the same though, because that middle step, that crucial step, is a Michael reaction. Here's the mechanism, kind of half version of a mechanism. That first part, making the enamine, we've seen this, chapter 19. I don't think this was one I had you guys remember for the test, but it's one we've talked about. We've seen it. Step number 2 then is the one we just looked at, the Michael reaction. So we have some resonance there in order to get to our enolate, and then we do our nucleophilic attack with a little bit of rearrangement. And then our last step is the hydrolysis. So I said that hydrolysis is doing a couple things. It turns the enolate into an enol, and then the enol can tautomerize back into the ketone, but it also turns our enamine, or technically the form that it's in right now is an aminium ion. It's a enamine with a charge, essentially, though. It turns that back into our ketone. And that's actually a reaction we talked about back in chapter 19 too. We learned how to make an enamine, and then we learned how to get the enamine back off of our ketone. So I can't remember if I said this to you guys or if it was just the morning class, but a lot of these reactions start to look fairly complicated and complex because we're making bigger molecules, but we're really just taking reactions that we've learned in previous chapters, adding in one new piece, and kind of mushing them all together to make something new. So even though you don't need to know the mechanism, and I know I've said this a few times, but even though you don't need to know that full mechanism, seeing how these pieces break down can help you understand and remember where it's coming from. Question about the Stork reaction at all? Okay. Let's look at a practice Stork reaction. Now, if we aren't drawing out any intermediates or anything, the Stork reaction is pretty easy to draw out the products for. I'll show you what I mean. All right. So this is our Stork reaction. Again, it looks similar to a Michael reaction, but we know it's a Stork reaction for a couple reasons. One, we're starting with just an aldehyde. A Michael reaction has to start with a dicarbonyl. And we have an amine in there. So that right there, having the nitrogen group in there, is a dead giveaway that it's a Stork reaction. Here's how we're going to draw our product, though. I'm going to redraw my aldehyde on the top. And it's not that it has to be an aldehyde. I'm redrawing my carbonyl that doesn't have a double bond on the top. And I'm going to draw my double bonded carbon, my alpha beta unsaturated carbonyl on the bottom. The new bond that's going to form goes from alpha to beta, and that's it. We're going to draw that new bond, and we're going to delete the double bond. So there's my new bond. Actually, I'm just going to put a little X over it because I'm going to redraw it. And then we get rid of that double bond. So here's our final product. And if we have the product, we want to double check. We can always count. 1, 2, 3, 4, 5. We've made a 1,5 dicarbonyl. So that helps tell us that it fits into the definition of what a Stork reaction should produce. We're getting that 1,5 dicarbonyl as a product. Any questions about that reaction? Okay. We have one more reaction in this chapter then. Our last reaction is called a Robinson annulation. Annulation is a fancy way to say that it's going to make a ring. So Robinson reaction. And look at that second bullet point. It's already telling us that this is going to be a Michael reaction combined with an intramolecular aldol condensation. So 2 new reactions, but it kind of means that it's not a brand new reaction. We're just combining 2 things that we already know. So to do our Michael reaction, we need a 1,3-dicarbonyl. So that's our Michael donor. Remember, that's our nucleophile. And we're going to react it with an alpha, beta, unsaturated carbonyl. This is our electrophile. We're reacting it with base. That's it. The base is going to remove that alpha hydrogen, and the new bond that's going to happen, this is all that's going to happen. We're going to go from the alpha of one to the beta of the other, and we're going to get rid of that double bond. So this is our 1,5-dicarbonyl. This is the product of the Michael reaction. Then in the second half, we're going to do the intramolecular aldol condensation. So we still have base, we have some heat in there to help the reaction. That base is going to take off this alpha hydrogen. So the alpha carbon that's on the end of our alpha beta unsaturated carbonyl, it's going to remove that hydrogen. And then if you remember back, I think the aldol reaction was the first one we did in this chapter, but that is going to attack our carbonyl, which will become a negatively charged oxygen. So here's what we get.
Professor, with these reactions, most of the time when we would have things be attacking the ketones and stuff like that, it would be a backside attack. Is the 3D orientation of like these molecules still allow for that, where like the oxygen could be up and then, I don't know, because all of the rest of them have free rotation around their bonds, they can still get a backside attack?
Yes, it does still allow for that. And this one is very specific. The reason why this works is, remember what we're forming is a 1,5-dicarbonyl, which means that the alpha carbon is carbon number 6. So when we do that nucleophilic attack, we're going to form a 6-membered ring. 6-membered rings have really good bond angles. So as that chain, carbons 3, 4, 5, 6, as that chain is kind of moving around, it will easily move around and make a connection to that carbonyl carbon because it has the right bond angles. If that chain was too short or too long, it wouldn't have the right angles to make that match. So because it has just the right number, though, it's definitely very possible to do that. So we end up with a negatively charged oxygen after that step, after that nucleophilic attack. And then we're going to have a couple things happen. But if you remember back when we talked about aldol, we had an aldol addition reaction, which really just means, let me switch colors again here, which really just means we put a hydrogen right here. So this would be an aldol addition reaction. Because it has heat in there, what we do is a dehydration reaction. So we are removing the hydrogen from the alpha carbon. We're removing that alcohol, and in its place is this double bond. And that's what gives us the aldol condensation reaction is that double bond. This one is definitely the most complex out of all the ones we're looking at. We are using two new reactions to kind of create this morph together third reaction. But again, if we learn about Michael first and we learn about the Aldol first and then go back and revisit Robinson, it will help it to make a little bit more sense. The bottom of this slide is showing us a retrosynthesis. So meaning this is what we want to make through a Robinson reaction. What do we have to start with? A couple things. Because we know it's a Robinson reaction, we know that we have to have a 1,3 dicarbonyl and we have to have an alpha beta unsaturated carbonyl. And then from there, we have to figure out what bonds we need to break. The 6-membered ring is what formed during the reaction. So if we look at that 6-membered ring and break the double bond and break the bond between the beta and the gamma carbons, so I'm going to use the terms left and right here based off of how this one's drawn. But for this one, that means that the left-hand side is my Michael acceptor. It is our alpha beta unsaturated. And then the right-hand side is my 1,3 dicarbonyl. And yeah, the other carbonyl isn't on there because during the reaction it was broken off. But wherever that pi bond is attached, that's where we need to replace it with a carbonyl. So we are going to do a retrosynthesis with this. I'm going to draw our product. Okay. And we're filling in our pieces over here. We know that it's a Robinson reaction. We're told that. So again, looking at this, knowing the handful of reactions we've talked about today, if I just gave you this, you could fit it into a lot of different boxes. So I will tell you this is a Robinson reaction. So because it's a Robinson reaction, we know that we need base and heat. That's our only reagents that we need. We know that we're going to need, I'm going to divide this in half, but I don't know if I'm going to give myself enough room. We know that we need a 1,3 dicarbonyl. And we know that we need an alpha beta unsaturated carbonyl. So we kind of have to undo this reaction to get back to the starting place. I know that I'm going to break this bond. And because that is alpha and beta to this carbon, I know that the left-hand side of this structure is going to be my alpha beta unsaturated carbonyl, which means that I'm also going to break this beta gamma bond. So I'm going to draw that in green over here, and I'm going to keep the angles the same, so it's going to look a little bit weird.
Professor, what was the left side again?
That's my alpha beta unsaturated carbonyl.
Okay, thank you.
I'm going to do the other side in another color. So we break those two bonds. And as we break those two bonds, this needs to be my pi bond in my starting material and my reactant, but the rest of it essentially stays the same. And then on the other half, if that was my alpha beta unsaturated, then the other half has to be my 1,3 dicarbonyl. And I'm going to draw that carbon structure. And again, I'm going to keep the bond angles the same. Wherever we broke off that pi bond, that needs to be the second carbonyl. I'm hesitating because I drew my angles a little bit different here. And I'm going to put a hydrogen here because it is an aldehyde, and generally we include that hydrogen with an aldehyde. But that's where our carbonyl would go. So we're breaking the pi bond, and then that pi bond had to have formed alpha and beta to the alpha beta unsaturated carbonyl. So notice that if we compared it to the other carbonyl, it's on the beta and gamma carbons. So that means that that one, the one that it's beta and gamma to, has to be our 1,3 dicarbonyl. Does that make sense? Do we have questions about that? It takes practice. It's one of these things that I hesitate a little bit on how to explain it because I want to make it useful, but I also don't want to simplify it too much that my explanation doesn't apply to everything. Because yeah, if you just memorize a pattern, we all know that it just doesn't always work. So yeah. Questions about that? Okay. And then anytime you do the retrosynthesis, I definitely recommend going back through and counting all of your carbons, making sure that the total number of carbons that you started with and end with are the same. It's easy to leave out a substituent, especially like this methyl group right here. It would be easy to leave that out because it's not really part of the reaction, so it'd just be kind of easy to forget it. All right, the last section in this chapter, the last slide, is looking at the synthesis. So essentially looking at, well, if we do an aldol or a claisen, or if we do a stork or a Michael, I'm going to add Michael up here. What that is, not an M. Here we go. Or a Michael. We'll get that 1,5 dicarbonyl, and aldol and claisen give us a 1,3. So it's just kind of giving you a good label for the products. And we talked about this as we went through them, but that can be a way to help you identify what's forming. All right, we are going to start chapter 22 today. Any questions about chapter 21 though before we switch over? All right, I'm going to switch slides then. Here's 22. I'm knocking my headphones off. Let's go back up here. We're not going to get very far into this chapter, but I want to make sure that we get far enough into it that we'll be able to finish on Wednesday. Oh, let's see. Let me try something else. My mouse was not showing up very nicely. 22. There we go. That's better. There we go. So this is our last chapter. This is our last chapter of the semester, which means it's also your last chapter of organic chemistry. I think that we're ending with one of the easier ones for sure. It is amines. We've talked about amines a couple times here and there, which means that chunks of this chapter are going to feel like review. It is a smelly chapter. We'll get to that. You don't need to know any of the mechanisms for this chapter because really the ones that, I know, me either. the mechanisms that you would need to know, we've already talked about in past chapters. So this one is really kind of a flashcard chapter. So what we're going to cover today are the first, I think it ends up being first 8 slides. So really it's just kind of like introduction and properties, nomenclature, like that kind of stuff. So we know what an amine is, but just to get the official definition out of the way, it is a nitrogen that has one or more R groups attached to it. Primary, secondary, or tertiary, based on how many R groups are attached to it. If it has no R groups attached to it, then that makes it ammonia. Ammonium is when we have 4 groups attached to it. So even if those were R groups, we could refer to it as an ammonium-based nitrogen. Really, it just means it's a nitrogen with a charge and 4 things. Nitrogens are really common in nature. So a couple examples down here: serotonin, adrenaline, caffeine, morphine, and codeine. So notice that they have INE as the ending for a lot of them, like an amine does. So nicotine also falls into this list. Something else I was thinking of earlier, I don't remember. I like things like this, though, the morphine and the codeine. So, I mean, essentially they do the same thing. Morphine and codeine, they're both painkillers to a certain extent, different levels. But the only difference is this R group here. With morphine, it's a hydrogen, and with codeine, it's a methyl group. So I always find that fascinating. I feel like sometimes I should have gone into pharmaceutical, because things like that and the huge difference they cause in your body is so weird to me. And I know nothing about biology. So it's just like that side is magic to me. That side of chemistry is magic. Amines can be bases and nucleophiles. And really, bases and nuclei, I don't really want to go back to school. But you're right. It is not too late for sure. Amines can do both jobs. So when they act as a base, it means that they're using their electrons to grab onto a hydrogen. When they're acting as a nucleophile, they're using those electrons to grab onto something that's not a hydrogen. That's really the only difference. So when we talk about a proton transfer or a nucleophilic attack, it's the same process. It's just whether or not our electrophile is a hydrogen or not a hydrogen. It's the only difference. A little bit of nomenclature. If they are simple primary amines, we treat the nitrogen as the parent chain. So we just list whatever's attached to it and then the word amine. When they are more complex, then the word amine becomes part of that parent chain. So the one that's down here, we have a 7-carbon chain. The nitrogen is on carbon 2. So our parent name becomes 2-heptanamine. I think specifically with amines, the way it is pronounced can be a little bit, it sounds almost a little awkward, because we have the heptanamine, we have the an and the amine back to back. But remember, every syllable has a job. So the hept is telling us that there's 7 carbons. The an is telling us that it's all single bonds. And then the amine is telling us that there's a nitrogen. So don't just mush it into heptamine. That an has to be in the middle there. Same rules as always. We want to have the longest parent chain that contains the functional group, lowest numbers. If we have a functional group like an amine, it gets the lowest number automatically, regardless of, well, I should be careful how I say that. The highest priority functional group gets the lowest number possible, regardless of what just regular substituents are on the chain or the ring, and regardless of where they're at. And then we just attach everything in alphabetical order as we name it. So that's what this one is even referring to up here. Nitrogens are pretty low on that priority list that we've looked at. So if we have something else, then our amine becomes amino, and we put it as a prefix. We've also talked about aniline. That was one of our substituted benzene common names that we had to learn. And then the last thing that's on here is when we have substituents coming off of our amines. And we've essentially talked about this because we talked about amides. So when we do that, we just add a capital N in the front of the substituent to say where it's located. One thing that I do want to bring up, because this was something I saw in the test. So I can't remember if you guys or the other class had to name an amide. Actually, I think you guys both did. I think I put it on both tests. But when we're alphabetizing, we are still alphabetizing based off of the substituent. So in this case, it's the C for chloro, E for ethyl, M for methyl. We don't use ditri or tetra. And the fact that they're attached to a nitrogen doesn't affect the alphabetizing. That's what we call a locant. It's telling us where it's located, but it doesn't affect that alphabetizing. So I saw a handful of people either put it in the very front or the very back, but didn't actually alphabetize them. So just to point that out. All right, let's do one little practice one with this. Draw something here. Okay, that's good. Where are we going to start numbering this thing?
Maybe one at the amine group.
Yeah, so right where that nitrogen's attached. So 1, 2, 3, 4, 5, 6. And I went clockwise so that the other substituent would be at the lowest number possible. So even though we want our functional group to be at the lowest number possible, we still want to look at where the other ones are located, especially when it's in a ring, because we have a choice of going either direction. So our parent name for this then would be cyclohexanamine. We don't have to put the 1 in there. When it's in a ring, it will be at carbon number 1. So this is totally optional. I think sometimes with tests, it's nice for your own sake of mind to put it in there. So then if you're like reviewing your answers, you see the number, you know you didn't forget anything. If it's not in there, you might just think you forgot something. I have 3 substituents then. We have 1, 2, and 3. What's going to come first alphabetically?
The ethyl group.
I don't think we have an ethyl group. We have methyl.
Oh, just kidding.
And then we have a propyl. Yeah. So we're going to put that methyl first. So when we have 2 things, 2 of the same thing, we just have to say where they're both located. So they do both happen to be on the nitrogen. So we're just going to say NN dimethyl and then 3-propyl. And then what do I need in the very front of the name? What am I forgetting?
You're going to need a 1R and then a 3R.
So we're going to check to make sure that that's right before I circle it and sign off on it. But what's another way to say this that takes a lot less work?
Just RR?
Not really. If you have more than one stereo center, you have to have the numbers in there.
Gotcha.
1, 3R.
So what's another way to talk about the stereochemistry with this ring without using R's and S's?
Oh,
Cis or trans?
Yeah, so is this cis or trans?
Trans.
trans. So we can do trans because we have one dash and one wedge. So if they were both wedges or both dashes, we could call it cis. It definitely takes a lot less effort. But using R's and S's is correct. So let's double check what I have on the screen. So number 1, carbon, the nitrogen would definitely be highest priority, 1, 2, 3. So I agree that it is an R. And then on the other one, our high priority would be right here. 1, 2, 3. 1, 2, 3. So it's going to the left, but it's backwards. So yes, those would be the correct labels. So we could write it as 1R, 3R, or trans, and both are completely legit, both work. So a couple reminders on there and things we haven't seen in a while, but remember that final is going to be everything. So we got to do a little bit of refresher on stereochemistry. Questions about the naming at all?
Professor, I have a question about the naming from the test.
Yeah.
Okay, so I don't completely remember, so I might just ask you again if you don't know what I'm talking about. But one of the naming questions, I think it had an amine as a not a functional group, as like a substituent.
Mm-hmm.
And then the N and the amine part were like separated. I put them together on the test.
So we use the N to say what's attached to it. So we would say that N-methyl to say that there's a methyl attached to the nitrogen. Mm-hmm. But if we just had, like if we had a ketone on our ring, and then over here we just had a nitrogen group, we would call this 3-amino cyclohexanone. We wouldn't need an N in that if there wasn't anything attached to the nitrogen.
Okay. I might ask you again later because I'm not sure.
Okay. Yeah, you can come to lab and we can pull it up and look at it.
Okay, thank you.
Mm-hmm. All right. Random properties. Solubility, boiling point. If it's small, meaning 4 carbons or less, it will be soluble in water because it can hydrogen bond to the water. Primary and secondaries can hydrogen bonds with themselves, so molecules of the same type, which means they will have higher boiling points than a tertiary. Right here's a couple examples of that. Geometry. Our nitrogens have a lone pair, so they fall into the tetrahedral family, but that lone pair puts them in a trigonal pyramidal shape. And even if they have 4 different groups attached to them, they can actually interconvert. They can take their little shape and kind of flip upside down like a broken umbrella. And so they will always be racemic. They don't have one set stereochemistry. And as brought up earlier, they are stinky. A couple of the well, not necessarily common, but trimethylamine is a common one. It's a fishy smell. Ammonia itself is common. You probably know what that smells like. It's in a lot of cleaners. It's also in cat pee, so you probably have smelled ammonia. And then the other 2 that are on here are putrescine and cadaverine, which I just think have great names because they're named after putrid rotting meat and literally decomposing cadavers. And they are both diamines. They both have those 2 nitrogen groups on them. And then our last slide before we call it quits for today is looking at the basicity. So our nitrogen groups are pretty strong bases. When they are protonated, they are fairly weak acids. So we can use those nitrogens to remove hydrogens from whatever it is we're reacting with. This also makes them very easy to work with in the lab, because if we have excess amine in our solution, we can do an acid wash. It makes our nitrogen now have a positive charge. So if we have a positively charged nitrogen, and if we did an HCl wash, it has a chlorine. So we've essentially turned it into a salt, which makes it aqueous in the water layer. Ions are generally very soluble in water. And so that can now give us a way to separate it into the aqueous layer and get it out of the organic layer. So it's a great reagent for that purpose. I think we will start here. I got one last thing on there. It's going to take us longer than the minute we have left. So we will start with a little bit of delocalized electron talk on Wednesday, and then we will go through our reactions. So as I mentioned, I don't have any pre-lab lecture or anything for lab today because we already talked about it last week. You just have the last few weeks to work on your lab practical. But if you have questions about it or anything else, feel free to stop by and chat. And I will be in lab, or I will be in Zoom for all of lab today. So that is all. I will see you on Wednesday.
Thank you, Professor.
Thank you, guys.